So let's take the next step and create a layer of neurons and then also different layers of neurons and also link them together. So in the last part, we're just looking at our data matrix. And I was saying that usually, of course, we have not only one data point, we have many different data points. So our input is a matrix where usually the rows correspond to the number of data points and the columns to the features, so the length of the input, so to say, or how many dimensions every data point has. And we created a function and ran our function, but now we want to create a class for our layer, and we want to set the weight bias in the output as a so-called attribute. And I want to explain, of course, how that works and what the idea behind the structure is, and that in fact we will have some advantages over the normal function that we created earlier if we just create the class. Because at the end, we want to create an entire module for our neural network, and this module will contain different classes, and among them there will be the layer, and there will be other things like optimizer, and so on. And also for the backpropagation, we need in different classes. So just from the programming point of view, it makes more sense now to create an own class for these layers. And there are different variables now. So I would denote n inputs as the number of features per observation. So it's not the number of inputs, so it's the number of features. And neurons will be still the number of neurons. Why is n data points not an input variable? Well, if you think about it, it actually doesn't make sense if the number of data points is an input variable, because the structure of the network should actually not depend on how many data points I have, but it should depend, of course, on how many features every data point has, because that refers to the complexity of the data set, so to say, but not the number of data points should matter. So therefore, n underscore inputs does not refer to the number of data points, but refers to the number of features. So if we just take a look at our matrix, so again, that's our data matrix. The rows correspond to data points and the columns to the different features. And we want to now multiply this with our network. So what we still have to do is that if we just pick one neuron, that we have to compute the dot product here. So for example, this particular column with this particular row. And if we just turn it this way, then the number of neurons now would correspond to the number of columns and the different weights to the number of rows. So every column you see here would correspond to one particular neuron. So what happens then is that we compute the dot product for every neuron to every data point. So we just multiply these two vectors and we will just get one value. So that's essentially just the sum that we discussed earlier. And these are two matrices, and according to the rules of matrix multiplication, that will just continue along the different rows. That means it will continue along the different data points. So this neuron then calculates the output for all the different data points until it reaches the end of our matrix. And then the next neuron will do the exact same thing. So at the end, we will have a matrix as an output, so not just a number and also not just a vector, it will be an entire matrix. And the size or the shape of the matrix will correspond to the number of neurons and to the number of data points. So the columns then, if you arrange it this way, will correspond to the number of neurons, and the rows will correspond to the number of data points. That actually makes sense because this length here should be conserved, because that is just how every neuron responds to all the data points. So for every data point, I should have a response from all the different neurons. And that's what I actually see here. So if I just take the first data point, which is here, I will have the response from all the different neurons to this particular data point. And that's always something I would recommend if you just set up these different layers, and also if you have high dimensional matrices then later. Just think about the orientation and the shape, whether it makes sense. And then always, of course, check the output whether it has the same structure that you expected to have. So like in this case, when we generate the output, it should have the shape number of neurons times number of data points. And you can still perform this with NP dot, even though it's strictly speaking not an actual dot product, but you can see it as a sequence of many different dot products. So you can use NP dot if you just multiply the inputs with the weights. So we have to turn this into a code. And therefore, I would recommend, as I said, to set up a so-called class that we want to call layer dense. So dense just refers to the connections so that every neuron is connected with every other neuron in the next layer. And that's why we call it layer dense. And we have to initialize this layer. So therefore, we set up a method, so-called init method, which is pretty common. If we just call this particular class, it will create a so-called instance, and I will show you how that works, what it actually means. And when we call it, it just sets up the layer with the required size. So n inputs, as I say, does not refer to the number of data points, but to the number of features. And then here we have the number of neurons. And then we initialize the weights, again with a random number generator. And we can also initialize the biases, in principle also with a random number generator. But you can also do this with NP zeros. So the syntax is just slightly different because you have to give the shape of the matrix. In our case, it's a 1 times n neurons vector, because every neuron has one bias. So that will be a vector with a number where the number of columns corresponds to the number of neurons. And then we also want to set up a method that we just call forward, where we actually feed in the actual inputs. And in this forward, so-called forward pass, we're going to perform the actual calculation and where we calculate the actual output. And it's called forward pass because that's where you feed in the input data and you will pass it on to the next layer and so on and so on. And that's why we call it forward pass. So therefore, let's now move to our user interface and set up our code. So first of all, I would recommend to open a new folder and we just call it number 2 layer of neurons. And we also navigate to this particular folder. And then we set up our class. So first of all, we have to import NumPy. And now we set up our class. So in principle, you could have an input argument here. We don't need it for now, but for other classes, we're going to need that. So and now let's define our first method. That's the init method, when we just call the class that it generates the network with the weights and the biases. So we define it with the init operator. And then there's this keyword self, which refers to its own class. And I will explain you what it means. And I also will show you what it actually means. So now we just ignore it and say, okay, it has to be part of the syntax, but you're going to see why we're going to need that. So what we need as an input argument is the number of features, so n inputs, and n neurons, so the number of neurons. And based on this, we're generating the weight matrix and the biases. And now you can kind of guess what self actually means. So it refers to its own class. So if we just set up the weight matrix, it's been saved in this class. Therefore, we can pass it on to another method within the same class. And we can also call it as a so-called attribute if we have generated an instance of this class and can also just look at these different values. And that's what we're also going to do, because we need to keep track of the orientation, the shape of the matrices. So let us first of all generate the matrix with a random number generator. And we can do the exact same thing with the biases. And yeah, you can do this with the random number generator again, or we can also do this with zeros, NP zeros. Their syntax is a bit different. So you have to give the shape as an input, and it has to be 1 times n neurons, because every neuron has 1 bias. So that will initialize the layer, and also will show you in a few seconds what it actually means. And now we need the so-called forward pass, where we feed in the information from the input, and we also want to pass this on to the next layer. So we have to generate an output. So we define the so-called forward pass. So when you see that forward is just a variable name, so to say, for the method, whereas init was an actual keyword. And also here, we need to refer to itself. And now we require the inputs as an input argument. So then we generate the output by just applying the dot product. And we have to multiply the inputs with the weights. And since we used self, it's been saved in this class. So we just can access it by calling it with self weights. And we can do the same thing with the biases. So we just copy and paste this here. So they've been saved in the class. And so we can pass it on. And we will also self the output. If you still don't understand the structure of the code to 100%, that's not a problem, because I'm going to show you now what all these parts, what they mean, what the purpose is. So let us first of all save this now, but now we don't want to save it under the name layer dense, because this will be the first part of our module. And we want to add a few more classes. So not only the layer, but also for optimization, for calculating loss and entropy. We want to add activation functions, the softmax layer, and so on. So we'll all write this in one particular module, which will be in our artificial neural network. And therefore, let's save it under the name, I don't know, my ANN, for example. So that's our module, my ANN. And this contains our class layer dense. And if we compile it, we can also call it now. So let me just close this part here. And let us just open a new file, because what we want to do now is that every time we add something to our module, we of course want to test it. So when we increase the complexity of our code, every time we add one more step, we also want to test whether it does the right thing. And our test routine will also increase continuously. So we'll actually always have almost the same lines of code in our test routine, and just always add 1 or 2 more lines according to our progress. And therefore, it doesn't really make sense to run everything in the console. It actually makes more sense to set up a new file. And let's just save it as test my ANN. Because if we just test it every time we add one more thing in the code, then we just make sure that everything makes sense and does the right thing. And it's way more complicated if we just do everything at once and then test it at the very end. And certainly there will be lots of bugs, and it's really hard to figure out where they come from and how to fix them. So we will just do this step by step. And that's why we want to set up such a test my ANN file. And the first thing, of course, we have to do is to import our module now. And if we just say then from, and if we just type my ANN, you see it should pop up now in the autocomplete. And it's also recognized as a module. That's what you can see here. So there's this little letter M, and it also says it's a module. And we want to import everything. So we just say import asterisk. That just means everything. And if we just run this, then you will also see that we have our module here. This module contains a class, which is called layer dense, and it has two methods, the init method for initializing the layer and also the forward method. And of course, we want to also create our input. And this time, we don't want to just create a vector, so like this. Some arbitrary numbers. We want to create a matrix. And in principle, of course, that has nothing to do with the ANN, so we can actually put it in front of our command here. So now we just create our input, and as you see, it's still a list, of course, but it has 2 data points, and every data point has 4 dimensions. So number of features, so n inputs is 4, but the number of data points is 2. And we also just want to turn this into an array. And of course, we need NumPy as well. So that we always just can run this routine as it is. So let me just do that again. So then we have an array. That's the same numbers, but now we have an array. All right. So now if we just run this from my ANN import everything, it should recognize our layer dense. And if we just call it layer dense, the autocomplete should recognize it. And it even shows you what the input arguments are. And we can just call this layer dense now and see what happens. So we just copy it to our test routine. So then it's just say layer dense, and the input argument was n inputs, which is again not the number of data points, just the number of features. And we can actually determine this with a shape if you like. So it's just i.shape. That's a so we need a second output. So it's S1, because Python counts from 0. And then next input argument was the number of neurons. Let's say we want to have 5 neurons. What it does now, it's initializing our layer. And what actually happens if I just call this? So let me just show this in the console again. It just says that it is a method that comes from a module that's called my_ANN. That's what it actually does. And then you have this cryptical combination of numbers and letters. And that just is an address to a location where it has been saved on your hard disk. And if you run this many times, for example, it always allocates this so-called instance to different locations on your hard disk. So that means these are so-called instances. They're all different instances And in principle, you can call as many instances as you want. And you can also do this in the loop, for example, and just call as many instances as you want. And you probably can see now why it makes sense to have such a structure. And of course, we want to save it to a variable name, so let's just call it dense. And you can also see it here in the variable explorer. It just says layer dense, and it's an object. And if you just do that and use the autocomplete, then you see that now it has these different attributes, biases, forward, in weights. And why is that so? Because when you call this instance, so like what we did here, it runs the init, and it says in the init that it just creates the weights and the biases. That's why we can access now the weights and the biases. If we just use the autocomplete, we can just take a look at them. And it fully makes sense now because we have, for every feature, we have a value, and for every neuron, we have a value. And I think you can also see what self refers to now, because self then just stands for the class, and then you have name of your particular object for your instance, for example. And also let's check the biases, whether it makes sense. All right. So, but now, of course, we have to call this forward method. And if we do that, it also tells us what the required input is. And in our case, of course, it's the input. So our routine, our test routine, will be this here. So we generate the forward part when we just call it, and then we feed in the input. And if we do that according to our class, it should also create this output here. So if we call the forward part, it should create the output, and let's see whether it does it. So there's no error message. So that means from the syntax, there's nothing wrong, but still we have to check whether the output has the orientation that we wanted to have. And remember, the number of neurons should correspond to the number of columns and the number of data points to the number of rows. So we have 2 data points, we have 5 neurons, so it should be a 2 times 5 matrix. So then we just call the output, and it's a 2 times 5 matrix, so it fully makes sense. Then let's go back to our PowerPoint. All right, so we created this code. We feed in the input, and then we just create our layer dense. So here with these numbers, it's hard-coded that you really see where it comes from. So we have an input with 4 different features. So the first input argument was n_inputs, which is the number of features. So it must be 4 in our case. Then we have the number of neurons, which is 3. So we call this layer by initializing the layer. Then we have the so-called instance, which has the forward part. So we feed in our input, and it generates an output. And now we can, with this structure, we can easily link these different layers. And I want to show you how that works. So we determined the shape of the input. That's what we did already. And as I said, the important part here is that the number of features and not the number of data points. And we can do this with shape. Then we create our first layer, and we want to call it dense 1. And we have the number of neurons. And then we have to call the second layer, and we can also call a third layer, and so on. And how do we pass on the information then? So first of all, did it make sense from the structure of our matrices? If we initialize the second layer, n inputs has to be n neurons of the first layer, so that the matrix multiplication makes sense. Why is it so? So let me just go back to our user interface. You can see why it has to be this way, because this is the output here of the first layer, and we have to pass it on to the next layer. So dense output here is the input for the forward part of the next layer. So therefore, if we initialize the next layer, our n inputs has to correspond to the size, to the shape of this output. And if it's corresponding to the columns, which is here, this is the number of columns from the output, and it's 5. Why is it 5? Because that's how we set up our neural net or our dense layer in the first place with 5 different neurons. So it's generating an output matrix with 5 different columns, and this will be the input for the next matrix. And since this is the shape or the number of columns of the input, this also has to be the number of columns for the input. So just let me just write this down again. So we want to set up the number of neurons, let's say n underscore neurons. And let's say that's 5. So I want you to see the entire code, so I scroll a bit further up. So that's the number of neurons. And that generates the first dense layer. And if I want to call the second layer and want to link it to the first layer, what do I have to do then? So again, the first layer will create an output that has the shape number of data points times number of neurons. So that will be our S1 here. So the number of columns. And the number of columns is the number of neurons in the first layer. So that's what we can see immediately if we look at the structure. So we have to do that, otherwise the shapes and the size of the matrices don't match. And now we're also generating a second layer. And you see again, the second input variable is completely free. So as it was here in our first layer as well. So we can also say that we have two different numbers of neurons. So n neurons 1, for example. So let's call it n neurons 1. And then we have n neurons 2. And that could be anything, right? For example, let's say 6 or something. So we have the number of neurons here in the first layer. And that has to match the number of inputs here, right? Because it's generating an output matrix, which has as many features as neurons we had in the previous layer. And then we are completely free for the second input argument. But if we want to pass it on to the next layer, let's say dense 3, then again, this has to be the first input argument. So that's how we have to initialize our layers, first of all, and then we can just pass it on. So let us also just do that so that we have an idea about the structure. So we just create, we just define that we have in the first layer 5 different neurons. In the second layer, we have 6 neurons. So we just define these variables, of course. And then we define these layers. And we can also just check again. we, for example, look at the number of biases, so how many biases should we have now? Well, it should be n neuron 2, so that should be 6. And we have 6 biases. If we take a look at the first dense layer, n neuron 1 was 5, so this should be 5. And you see you have 5 biases. And now we have to link them together. So our first dense layer gets the actual input, and it generates the output. And again, what is the size or the shape of the output? So let's generate the output again. So it has the size number of data points times number of neurons from the first layer. And this will be the input for the next layer. So this is the input for the next layer. So we just say then dense 2, because that's the next layer. We feed this into the forward part, and it should be our input. But the input is the output of the previous layer. And since we have initialized the size of these matrices accordingly, that should actually work. So we don't get an error message, but still we want to check whether the output matrix has the correct orientation. And what should be the size of the output matrix? Well, let's think about it. So the output is the input for the next layer. So we should have as many rows as inputs, so as many as data points. It should be 2. But then we have the number of neurons, which is 6. So every neuron should contribute to the input. So this should be a 2 times 6 matrix. And let's see whether we get this. So let me just call the output. And here you can see it. It's 2 times 6. 1, 2, 3, 4, 5, 6. So it all makes sense. So we can also just add this here. So we can just say it's out, and then we have dense 2 output, and we can just look at the shape. Of course, I have to generate the output first. And here we go. So it's 2 times 6. And that's what I meant with testing. So we will set up some arbitrary numbers for the input and also for the number of neurons. Then we call our module. Then we call the different instances of our classes. And then we just play around a bit with the matrices and see whether they make sense. So again, let me just repeat what we did. So we just called with one class different instances. So we just called the layers of different sizes. And we can just really pick any size of the layers. It has to fit to the input, but not to the number of data points, but to the number of features. Then I'm free to choose the number of neurons for the first layer, but that generates an output which has the size or the shape number of data points times number of neurons. So therefore, the first input argument for the next dense layer has to be the number of neurons we had in the first layer, but then we are free for the number of neurons in the second layer, and so we can pass this on. And if that's still confusing, I will show you this graphically, of course. So what we did here is that we first of all, let me just go to the slides. So we created our input, then we determined the shape of our input, and then we created the different layers. So for example, if the first layer has 3 neurons, then I need to initialize the second layer with 3 as the first input argument. And why is that so? That's what you see here. So we have 4 features for every data point, but we have 3 neurons. So that's what we have here. And every neuron from the first layer has to talk to every other neuron from the second layer. And in this case, so I kept it simple. The second layer has only 2 neurons, so that you can really see it in the plot. And again, you can see why it's called a dense layer, because every neuron from the first layer communicates with every neuron from the second layer. And so then we generated the instances, so we can feed in the forward part to the first dense layer that creates an output, and the output of the first dense layer is the input of the second dense layer. So we have created an actual network. We have 2 different layers, and we also know how to link them together. And I hope you also see how we can link n different layers together. We just have to make sure that these numbers here work. But however, the second input argument, that's always 3, because that determines the size of the layer in the next step. All right. So, and now since we know how to link layers, we are ready for activation functions.